Welcome to part 3 of our introductory lecture on base R programming. In this part, we're going to cover functions and control flow. There are quite a few references for this section, and as usual, these are mostly extra reading rather than required material. But if you want some more background on what I'm going to be discussing, you can take a look at the book Hands-on Programming with R. You can also take a look at the chapter on functions from the Tidyverse Style Guide and from the book R for Data Science, as well as the chapters Control Flow and Functions from Advanced R. All of these links are on the lecture slides, and all of the relevant books are freely available online, so you can visit the course website, click on them, and read to your heart's content. We're going to start off with functions. Now we've covered the very basics of our syntax, and we're ready to actually start doing some programming. So what is a function? Why do we want to use it? And when do we want to use it? Well, a function is a chunk of code that encapsulates a particular task so that you never have to program that task from scratch ever again. And functions embody a crucial idea called abstraction. Roughly speaking, abstraction means that the user of a function, which by the way includes your future self, only needs to know the inputs and outputs of the function. In other words, what the function expects you to provide it and what the function is going to give you back. The user does not have to know how the function works on the inside. This is extremely valuable. So using functions allows us to increase our productivity. So rather than repeating ourselves, we can automate. It also means that there are going to be many fewer copy-paste errors, and we'll end up writing code that is much easier to understand. I don't know about you, but I have had the misfortune of reading some stata_do files in my time that involve thousands of lines of what appear to be copied and pasted chunks of code that do more or less the same thing a dozen or more times. This is not only really hard to read, it's really cumbersome to write, and it's altogether too easy to introduce mistakes. So, a good rule of thumb, according to Hadley Wickham, is to consider writing a function whenever you've copied and pasted a block of code more than twice. And here's an example. Computing a z-score. So let's remember the definition of a sample z-score. We take some data, x, xi, and we subtract the sample mean x bar and divide by the sample standard deviation, little s. Now, R does have a function to compute z-scores. That function is called scale. But let's suppose, for the sake of argument, that it did not have such a function. We compute z-scores all the time, and we might like to avoid doing it from scratch every time. So now I'm going to show you the answer. I'm going to show you the result. Here is my function to compute a z-score. I'll then back up and tell you how it works. So at the top of the slide, in these 4 lines of code, is my function. Let's step through it. First, I give my function a meaningful name, and I use snake case as indicated by the Tidyverse Style Guide. So I have z with an underscore score. So z-score gets. What does that mean? That means, hey R, I'm creating something, and I'd like to call that something z-score. That's step 1. Step 2 is to specify the function arguments. So we do that by using the keyword function, some parentheses, and then we put in our argument. An argument means an input. It doesn't mean a quarrel or a, okay, I thought that was going to be funny, but it isn't. The point is, an argument is a synonym for an input. So hey R, this something, you know the thing I just told you the name of, z-score? It's a function, and it has one input. That input is called x. Next, we enclose the body of the function in curly braces. The body is the stuff that actually does all the work, the stuff that's actually going to compute the z-score. So I have my 2 curly braces. I have one at the top, and I have one at the bottom. Now, you'll see that I've added a space after that after the closing parenthesis of function x. That's not mandatory for the code to run, but it is good style. So one of the things that I really don't want to see when I'm marking your assignments is code that has no spaces, has no line breaks, and is hard to read. We want to have code that follows the tidyverse style guide, not because I'm being difficult, but because that style guide embodies lots of best practices to make our lives easier. So on this slide and on all of my slides, I abide by that style guide. And in that style guide, we put spaces after the function keyword and before the curly brace. Then we have a line break and we start writing the body of the function. Step 4, I'm going to write the function body. Again, this is the code that actually does all the work. It can be good to add some comment explaining the purpose of the function, inputs, outputs. If you want to get really fancy, there's something called Roxygen2 you can use to generate really fully detailed documentation for all your functions. But let's crawl before we can walk, certainly before we can run. And now I'll just add a simple comment that explains what this function does, what it takes as an input argument, and what it returns. By default, R returns the last evaluated expression. So what is an evaluated expression? Well, it's an expression that doesn't assign something. It's an expression, as you can see in line 3, that doesn't assign a value to anything. If you were to type that in at the terminal and you had some object X available in memory, that would just print out an answer. So that's an evaluated expression. And R is going to return the last evaluated expression in the function body by default. So in many languages, you need to use an explicit return statement. R does have a return statement, but it's considered bad style to use it, except for what are called early returns. We'll see some examples of those later. But you'll notice that in my function at the top of the slide, I am not using return. But what I can use is the z-score function itself. So here it is again. Now I'm going to create a vector of data, -2, 6, 3, and so on. And I'm going to compute the z-scores. So what is my function doing? Well, it takes that vector x, it subtracts the mean, and divides by the standard deviation. So now I end up with something that is centered and scaled. This z would have a sum of 0, and if I calculated its standard deviation, it would be 1. Now I'd like to distinguish between two things. First of these is the function definition. That's where I say z-score gets function of x, curly braces. That's where I tell R, hey R, I'd like to define a function. It's called z-score. It takes the argument x, and here's what that function should do. A function definition is where you set up the code that is going to be used whenever you call the function. So calling a function means actually applying it to get some kind of an answer or to do some real work. So towards the bottom of the code block, you'll see my function call, z-score, parentheses, example underscore data. So what I've done is I've passed example underscore data as the input argument to the function. And now I'm going to take example data and carry out the steps. Subtract the mean, divide by the standard deviation. So we just learned about the function keyword. When you're defining a function in R, you use the name, gets, and then function input arguments. But there's actually some shorthand that was introduced in R version 4.1. And that shorthand is as follows. It's a backslash and 2 parentheses. So if you don't want to type out that whole word function and you're using a modern version of R, which you should be, always use the latest and greatest version, you can just put a slash. And that will do exactly the same thing as the word function in this context. So we say z-score gets, but rather than typing function, we put slash. And again, we have parentheses and we specify the input arguments. Everything else is exactly the same. You might wonder, why would I want to do this? Am I just lazy? I don't want to type. Well, it's convenient in some situations, in particular when you're creating what's called an anonymous function. There will be more on that in a later lecture. But for now, you can just think of it as synonymous with the word function. And indeed, it is synonymous with the word function. Functions don't have to take only one input argument. They can take more than one. They can even take none. But most useful functions will take at least one. So the kth raw moment of a random variable is defined as the expectation of that random variable raised to the power k. The sample analog of the kth raw moment is the sample mean of the kth power of the observations. So if I wanted to create a function to compute raw moments, I could do so as follows. Raw underscore moment gets function of x comma k, then my curly braces, and inside of there I've got the function arguments, mean of x to the k. Here I am relying on R's vectorization. So if I'm going to pass in k a scalar, then x to the k will raise every element of x to the power k. I should be careful. R doesn't really have scalars, as I told you before, but if I pass in k of length 1, so a single number, I can raise the whole data set to that power. And then I'm going to take the mean of all those observations using the built-in R function mean. So let's test it out. And here we can apply raw moment to our example data with k equal to 1 in the first case, which gives us 2.3, with k equal to 2 in the second case, which gives us 21.3, and with k equal to 3 in the third, which gives us 101.5. So how do we supply arguments to a function? Well, there's two ways to do it. One way is by name, and another way is by position. On the previous slide, I showed you this line of code, raw moment of example data, comma 1, and the result was 2.3. This example shows us how we're passing arguments by position. So R looks at the order in which I supplied these things, example data and 1. And it says, okay, when the function was defined, I was told that the first input argument I'm going to get is called x. So that means that example data must be x. And I was told that the second input argument I'm going to get is 1. So that means that k must be 1. It then does the calculation with x equal to example data and k equal to 1. Another way to do the same thing is to explicitly specify the names of the function arguments. So here I'm going to tell R explicitly x is equal to example data. That is not an assignment statement. That is not an assignment statement. That is passing an argument into a function. It is saying, in this function R, I would like you to use example data as x. So in the role of x, I want you to feed in example data. Similarly, I want you to feed in 1 for k. The nice thing about matching arguments by name is I don't have to put them in any particular order. As long as I specify that k is equal to 1 and x is equal to example data, I can pass k first. Where I could get into trouble, however, is if I try to match arguments by position, but I get the order wrong. So here, what happened? Raw moment, 1 example data, and I got 1. Oops, what happened? Well, what happened here was that R thought that my data set, x, was just the number 1. And then it raised that to the power of whatever the first element of example data was, because it thought that was k. And then it computed the mean, giving us 1, which was not what we wanted. Now it's your turn. I have a somewhat lengthier and more interesting exercise for you. And as usual, now is a great time to pause the video and take your time working through this. At the top of the slide is a suggestion for how long it might take. You may need more time, you may need less time. That's all fine. Take as much time as you need. Pause, and before you resume the video, make sure to check your work against the solutions on the course website. Dot, dot, dot. It always introduces a measure of foreboding and a tone of disaster when we use these ellipses without further explanation. But fortunately in R, there's nothing bad happening when you have a dot, dot, dot. This is just a special argument that you can use in function definitions. It's a little bit exotic. You may not use it every day, but I just wanted to show it to you because it will turn up from time to time. So this is a special argument that you can use in your function definition, and it will allow the user to supply any number of additional arguments in a function call. These functions will actually be passed through to any functions that you have in the body of your function. If you want some more details on this, you can check out chapter 6.6 of Advanced R, but I'm going to show you a little example here. Now, the function mean in R actually takes a number of different arguments. One of the arguments it takes is called na.rm. So if you read the help file for the function mean, which you can do by typing $mean at the R console, you can see all of its arguments, and indeed one of them is na.rm. If you set na.rm to true when you use the function mean, then what R is going to do is drop any missing values before computing the average. By default, R doesn't do that because R's basic philosophy in life is check yourself before you wreck yourself, and it doesn't want you to blithely go around dropping observations willy-nilly. But sometimes we actually do want to drop missing values for some reason, and if so, we can specify the na.rm equals true option to the mean function. Now, in this context, the use of ... is allowing the user to specify that na.rm argument to my custom created function, raw moment, and that thing is going to just drop through and land inside of the call to the mean function. So let's see how this works in practice. I'm going to start off by constructing a vector of numeric data, 1, 2, 3, NA. Remember that NA means missing. I'm now going to use my function raw moment applied to some data with k is 1. The answer is NA. If I don't know the value of k, then it doesn't matter that I know the values of all the elements of x. I cannot compute the kth raw moment. So remember that NAs are typically contagious. Now, the reason this is happening is because when, actually, I just misspoke. Let me step back. I made a mistake. So let me correct my previous statement. Some data contains 1, 2, 3, NA. And I am now trying to raise that to the power 1. So I misspoke when I said that that k was an NA. That's not the case. So k is 1, and I'm raising each of those values, 1, 2, 3, and NA, to the power 1. So 1 to the power 1, that's 1. 2 to the power 1, that's 2. 3 to the power 1, that's 3. But NA to the power 1, well, that's actually NA. So when I try to compute the mean, I'm computing the mean of 1, 2, 3, and NA. But by default in R, the mean function is going to not drop NAs, but incorporate them. And if I ask R, hey R, what's the average of the numbers 1, 2, 3, and some other number that I'm not going to tell you? The only way it can answer is NA. And you can see that in the output just below the 6th line of code in that first block. But now using ... I can pass another argument into that mean function from my outer function raw moment. I can specify na.rm equals true, and this drops down into the mean command, so that now when R runs that mean command, it doesn't execute it with na.rm equal to false, which is the default behavior for mean. It does it with true. If you found this last slide extremely confusing, don't worry, it's not really the core of the course, and many of these things will start to become clearer as you get more experience playing around with R. But if you thought ... was confusing, you haven't seen anything yet. Unlike ... however, scope is pretty central to understanding how R works. So scope, very, very roughly speaking, refers to what objects a given chunk of code can see or can access. And I've got a little telescope here to remind you of that. So what you should think about is when you're looking through a telescope, you have a reduced field of vision. You can only see a narrow range of what's actually out there. So we want to ask which things are in scope, which things can a given chunk of code actually see. Scope is subtle and it's complicated, but it's also important. So I'm going to show you some examples of the key distinctions. But if you want some more details, you can consult Hands-on Programming with R Chapter 8 and also Advanced R Chapter 7. Okay, so here are some examples. Let's take a look at the first block of code. K gets 3. Here, K is being defined in what is called the global environment. So this means that the function just below, this function is called f, and I've defined f to be the function that raises x to the power k. This function can see k. In other words, it has access to that value. So if I try to run the command f of 2, it works. I get exactly what I was hoping to get, namely 2 to the 3, which is 8. So k is in the global environment. F can see it. It is within f's scope. Now in my second code block, I'm going to define m inside of the function g. Because m is defined inside g, the global environment can't see it. So if I try to raise 5 to the power m, it's not going to work. And the reason is that m is, in some sense, a variable that lives inside of the function g. Whereas in the previous example, k was a variable that lived outside of the function f. Here's another example. There is actually a built-in constant in R called pi. Here I am going to use this constant to construct a simple function that computes the sine of pi times x. So I'm going to define x is 0.5. Now I'm going to set up my function h. H is a function of x, and it's going to return sine of pi times x. Now I will compute h of 2. This returns sine of 2 times pi, which is 2. Notice that it does not return sine of pi times 0.5. What's going on here? Well, there are actually two objects named x. H is looking inside the function first. So when the function h is running, it looks inside the function and it finds x. Where does it find x? Well, that was the input argument. That was what was passed into the function. Since it's found x, it stops looking. The function h will only check the global environment if it can't find x within the function itself. That's a very short introduction to scope. But now we're going to move on to something that's a little bit more straightforward and no less important, namely if statements. And if you have programmed before, you will probably have seen these in your language of choice. If some particular logical condition is true, then I want you to run the code inside the curly braces. That's what if does in R and in most programming languages. So here are a couple of examples. If 3 is bigger than 5, print everything you know is wrong. Well, the message everything you know is wrong did not print because in fact 3 is greater than 5 is a false statement. My name gets Frank. If identical, my name Frank, print hi Frank. Well, that's going to print hi Frank because indeed the variable my name is identical to the character string Frank. Notice that when I write if, I follow the tidyverse style guide as always. So there is if, a space, and then parentheses. Then there's another space, and then the curly braces. These are the same kinds of curly braces that we used for the body of a function, and we format them in the same way. Again, the white space is not strictly speaking necessary. The code will still run, but it will be hard to read. And so we should always follow the tidyverse style guide to make our code much easier to understand. Quick warning. In an if statement, the logical condition must be of length 1. So it needs to be an individual true or false value. That's actually why in the 5th line of my second code example, I'm using identical my name, comma, Frank. You might be tempted to write something like my name equals Frank, but as I mentioned in an earlier part of this lecture, it can be quite dangerous to use double equals. This identical function is guaranteed to return a single true or false, which is exactly what we need inside of an if statement. Before I mentioned early returns, I said that in R, it is considered bad style to use an explicit return statement, except for early returns. Well, here is an example of an early return. And we're going to construct one using an if statement. So here's my function f. My function f is computing a sample variance. If you need to take a minute to look at line 5 of my code chunk to think about why this computes the sample variance, feel free to pause the video and do that now. It's well worth making sure that you understand everything in these little examples, because pretty soon we're going to be building much more complicated and interesting things. What I do here is I first of all check to make sure that x is not smaller than 2. Well, really, I'm checking to see if x is smaller than 2 in length. So if x has fewer than 2 elements, I actually have an early return. So I print cannot compute variance for fewer than 2 observations, because indeed you can't. If we do not, in fact, enter that if branch, then we do not hit that return statement. And instead, we execute the code in line 5. So let's test it out. In line 8 of that first code block, I have f of 1 to 3, and we get the variance of 1 to 3, which is 0.33333. If instead I apply f to the single number 2, the if statement is going to evaluate to true, and so I will reach the early return in line 3. Our displays cannot compute variance for fewer than 2 observations. And because we've returned, we never make it to line 5, so we never compute the variance. We've talked about if. Now we're ready to talk about else. What else does is adds a sort of a default case to an if statement. If a logical condition is true, then we're going to run the code in line 2 of the top block. Else, in other words, if that logical condition is not true, we're going to do whatever is in line 4 of this top block. So here's an example. If 3 is greater than 5, print everything you know is wrong. Else, print the laws of mathematics continue to apply. And I am relieved to notice that indeed the laws of mathematics continue to apply. Here's another example. My name gets Sam. If identical my name comma Frank, print hi Frank. Else, print you should change your name to Frank. And indeed, you should change your name to Frank. It's a great name. Something that is important to recognize about else is that the white space here actually is important. So if you look in each of the else statements on this slide, for example, line 3 of the top code block, you'll see I have the closing curly brace, a space, else, a space, and the opening curly brace. That's actually crucial that the else is on the same line as those 2 curly braces. You will run into problems if it's not. But there's more. There's if, there's else, and there's also else if. So we can use this to kind of go through a sort of a decision tree where we do one thing if A is true. We do another thing if A is false, but B is true. We do yet another thing if A and B are both false, but C is true. We do yet another thing if A, B, and C are all false, but D is true. And then if none of the above are true, in other words, if A, B, C, and D are all false, we do yet another thing. So the way that this works is we build up blocks of code, little chunks inside of curly braces. R starts at the top, and it looks for the first true condition. Once it finds a true, R skips the remaining blocks. If all of the conditions are false, and if there's an else block, then R is going to run the code that's inside of the else block. Here's a really simple example. I created a function of x and y. If x is bigger than y, we're going to print out x is bigger than y. Else, if x is smaller than y, we're going to print out y is bigger than x. Else, we're going to print out x is equal to y. And as you can see from the examples on the bottom of the slide, this functions as you would expect. The key here is that these are mutually exclusive cases. Here's what I might describe as an overgrown if tree. This is a function that computes numeric values for different pieces in chess, following a common convention that ranks a queen as worth 9 points, a rook as 5, a knight and a bishop as 3, and a pawn as 1. Now, this is a perfectly fine function. It checks if the x is a queen, a rook, a knight, a bishop, a pawn, or something else, but it's getting quite complicated. So we might wonder if there is sort of a simpler way to accomplish the same thing. And the answer is yes. So a very important idea, and an idea that takes a bit of getting used to, is what's called a lookup table. Excuse me. And the lookup table can be an alternative to an if tree. So here's a new function. I call it getValue2. Not really very inspired, but what can I say? It's late. This function behaves as follows. In line number 2, I create a vector called values, which contains the elements 9, 5, 3, 3, and 1. Then I assign names to all those values, following what we learned in our earlier segment of the lecture about atomic vectors. So now I'm going to associate the name queen with the 9, rook with the 5, and so on. In line 4 of the top code block, I have the statement values brackets x. So what's going on here? Let's take a look at what happens. If I run the command getValue queen, then I'm using the function from the previous slide, and it returns 9, because the value of a queen, according to this convention I'm using, is 9. Now let's see what happens if I run my new function, getValue2. It returns a 9 as well, but this time it also has a label that says queen. Okay, so what is the logic here, and how does it work? Well, we are relying on the fact that we can access elements of a vector by name in R. So in line 2 and 3 of my top code block, I create a named vector of values 9, 5, 3, 3, 1, with the names corresponding to these different chess pieces. So when I pass x into my function, the fourth line, values of x, is pulling out the appropriate values based on their names. This is what a lookup table is. It looks up the values using the names. As a general rule, if trees are best when you want to run different code in each branch, but lookup tables are when you want to assign different values or extract different values in each branch. Here is another exercise that you can try your hand at. There are some interesting examples here of code with errors and code with some complications you may want to think about. So as usual, take a few minutes, maybe 8 minutes, maybe more, maybe less. Try your hand at these examples, and then check your work against the solutions on the course website.